In this video, we're going to talk about, again, we're going to go back and talk about real versus ideal gases, and we're also going to talk about intermolecular forces and how they work to make gases act less ideal. And we're also going to talk about what these intermolecular forces are and how you can predict what the intermolecular force would be for a particular substance. So let's go back and review a little bit kinetic molecular theory. What kinetic molecular theory says about gases is it says that the molecules are small compared to the distance between them, that the molecules are moving very fast for a gas, and that the molecules have no attractive or repulsive forces between them in order for the gas to behave like an ideal gas. And the first bullet is to the condition that ideal gases need to be at low pressures. The second says that gases are at high temperatures. And the third talks about whether the molecule itself is polar or nonpolar. And ideal gases, gases that behave ideally, are typically nonpolar molecules. We can get polar molecules to behave like an ideal gas, but it would have to be at very low pressures. Oops, let me get my pen turned on here. It would have to be at very low pressures and at very high temperatures if the molecule is polar. If it's nonpolar, then it will behave ideally at slightly higher pressures and lower temperatures than the polar molecules. So let's talk about polar versus nonpolar molecules. And what I want you to remember is that polar bonds happen when we have an unequal sharing of electrons. And this results in a partial charge within the bond because we've got this unequal distribution, unequal sharing of electrons. Remember that polar molecules, again, overall unequal distribution, this is going to result in an end. We call that an end of a molecule that has a slight positive charge, and the end that is negatively charged, the end where all of the electrons are residing, will have a negative charge. And in order for a molecule to be polar, we have to have two things that will happen because we need this unequal distribution of electrons over. Okay, first off, a polar molecule must have a polar bond. No polar bond, all the electrons are equally shared, and therefore you cannot have a polar molecule. And one is that the polar molecule must have asymmetric polar bonds. If the molecule is symmetric, then we won't end up with an end that's positively charged and an end that is negatively charged. Overall, those will cancel out. And so let's do a couple of examples. And the first example that I want to do is methane. It is CH4. And we can draw the Lewis structure for methane. It looks like this. Again, remember these are three-dimensional molecules. Now, in order for the bond to be polar, I need an electronegativity difference greater than around somewhere between electronegativity, somewhere between 0.4 to 1.7. That will give me a polar bond. Okay, so carbon's electronegativity is 2.5, and hydrogen's electronegativity is 2.1, and that gives me an electronegativity difference of 0.4. And this is very, very slightly polar, but we would classify a 0.4 difference as non-polar bond. So then this molecule has to be non-polar. Okay? Let me put in molecule. All right, now the next one, let me go through and erase this. All right, the next molecule that we are going to talk about is, let me just add a, okay, there we go. The next one that we're going to talk about is carbon dioxide. And so let's draw what carbon dioxide looks like. Okay, now carbon has an electronegativity, again, of 2.5, and oxygen has an electronegativity of 3.5. This gives us an electronegativity difference of 1.0, so now we have polar bonds. So that is the first criteria that we need. But let's look at carbon dioxide. He is a linear molecule. So actually looking at him on flat paper is just fine. And so the oxygen has more electronegativity. So this guy right here, let me get a wider pen width. Here is going to be a region of electrons, and the electrons are going to go this way, right? The electrons are going to get pulled in that direction. And so this region is going to have what we call a partial negative charge, and we're going to have a partial negative charge here, and we're going to have a partial positive charge here. And this symbol that I drew is a small Greek letter delta. And what that means is this is a partial charge and not a full charge. This tells us that there is a density of electrons around that oxygen atom because he is more electronegative. So he fulfills the first part of whether or not he is a polar molecule because he does have polar bonds. However, do you see how carbon dioxide is a symmetric molecule? So he's very symmetric. And so overall, we will not have a positive end and a negative end because both ends of this molecule are negative, and the positive density is on the inside of this molecule. And so we would never see that. So he is symmetric, and so the molecule is non-polar. Okay? The next one that we're going to talk about, let's do another example. Let's do boron trifluoride. Okay, so if we draw the Lewis dot structure, oops, that's not hydrogen, that is fluorine. My bad. F, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4. Let's draw all these electrons. Okay, now, boron trifluoride, he has a steric number of 3, which means that he is going to be trigonal planar. So let's actually draw him like he looks. He's an F and a B and an F, not an H. Ugh. These aren't hydrogens, these are fluorines. Okay. And so he's going to look like this. He's going to have a bond angle of about 120 degrees. And let's look at the electronegativities. Boron has an electronegativity of 2.0. Fluorine has an electronegativity of 4.0. That gives us a difference of 2.0. So this guy actually is going to look more like an ionic compound. Okay, but let's look. Fluorine is going to pull all the electrons in this direction, right? The electrons are going to go there. Oops, let me erase this. And so it's going to be definitely, this is extremely polar, right? This gives us this guy right here, extremely polar. In fact, he's ionic. But again, he's flat. This is trigonal planar, meaning he's a flat molecule. So when we draw him on paper, that's what he looks like. And you can see that these guys are also very symmetric. And so therefore this is nonpolar. That these electrons, they all cancel each other out. All right, so we might ask, well, we've given you lots of examples of nonpolar molecules with polar or ionic bonds. Okay, the next one that we are going to do is, uh-oh, I hope this is... Okay, let's add another... Oh, I may have really messed this one up. All right, let's add another slide. The next example that we're going to look at is carbon tetrachloride. We have a chlorine, and another chlorine, and another chlorine. And so we know that the electronegativity of carbon is 2.5. Chlorine is 3.0. So this gives us a 0.5 difference in electronegativity. So these will have polar bonds. All right, but let's look at this in 3 dimensions. So we'll have a chlorine here, a carbon, a chlorine here. We have a chlorine coming out and a chlorine going back in. And the chlorine atoms are going to pull the electrons away from the carbon. And again, what we'll see is this partial negative charge in the shell and the partial positive charge in the center. And so what we have is we have a symmetric molecule which will result in a non-polar molecule. Now this nonpolar molecule will have polar bonds in it, and that's perfectly fine, but the polar bonds all cancel each other out. One is, let's look at CH2F2. Let's draw this guy. We have a hydrogen and a carbon and a hydrogen and a fluorine and a, oops, not an arrow, and a fluorine. So now let's look to see what he's going to look like in 3 dimensions. We have a hydrogen and this guy and this guy and the fluorines. And it really doesn't matter where you put these fluorines because it is three-dimensional. So as you rotate them, you can make any of the molecules that you build look like this one. If you want, when you come in on Monday and you want to build this guy and look at him and rotate him around so that you can see him in 3 dimensions, that's perfectly fine. So what we've got is we've got fluorine that's highly electronegative, so the electrons are all going to pull to this side of the fluorine, of this molecule. And so what we'll have is we'll have a non-symmetric polar bonds, and what this will result in is a polar molecule. Okay, and let's just go ahead and do one more example where we will have ammonia, NH3, and this is going to look like this. And let's draw this three-dimensionally. Okay, and what we've got is we've got these little lone electrons here, that this is going to result in a partial negative portion. And this guy right in here, these are all going to be partially positive. And so we absolutely have a polar molecule. Okay, so I've given you some examples on those. Take a look at them. And if you have any questions, I'll have office hours on Monday and I can answer those. Alright, so now let's talk about how these polar molecules, how we get some intermolecular forces arising from them. Place the existing recording. Okay, so what we've got is we've got some intermolecular forces. These are known as van der Waals forces. They were named after one of the scientists. I can't remember his first name. I believe he's Dutch. And so let's talk about, first off, intermolecular versus intramolecular. And intermolecular is between molecules, like interstate highways, international relations, between nations, international. Intramolecular is within a molecule, and we call these intramolecular forces, we call them bonds. We're going to talk about molecular. I will also abbreviate intermolecular forces as IM forces. All right, and so let's talk about what the phases of matter might look like on the molecular level. Okay, so if we have molecules that don't have enough energy to break the forces that hold them in place, we call these solids. And what we can say is when we talk about energy, remember that the average kinetic energy is related to the temperature. So if molecules don't have a lot of energy, they are at low temperatures. Okay, and so the phase of matter that's at low temperature is a solid. Now, as we add energy, so as energy is added, this means that we heat it up or raise the temperature. The molecules can overcome these intermolecular forces and eventually become gases. Now, there are two types of intermolecular forces. The first one that we're going to talk about are called dispersion forces or London forces. These forces are weak and temporary, and they result from temporary shifts of electrons within the electron cloud. So what it might look like is if we have a molecule here, let me draw down here for you. If I have a molecule here and a molecule here, okay, and I have some shifting of electrons that because they move around in the cloud, and so maybe the electrons might shift over here. And so what we would have is we would have a temporary partial negative charge here. That should be a small delta. Let me see if I can't make that look like a delta. Yeah, there we go. And then so on the right-hand side, we would have an absence of electrons, so that would be a partial positive charge over here. And what that can do is then for these to be attracted to each other, there would have to be a partial negative charge here and a partial positive charge here. And so they would be attracted to each other. But then the next second, the electrons might shift over to the right-hand side, so then I could have a molecule, then they could shift, and I would have a partial positive here and a partial negative here. Here's my nucleus, and the electrons could shift this way. And it would also be attracted to a partial positive charge here and a partial negative charge. And these happen all the time, and it happens very, very quickly. And so when these electrons move around within the electron cloud, they create these regions of partial positive and partial negative charges. And these London forces occur when the molecules are close together. And they're usually found in nonpolar molecules because they're very temporary. Very, very weak. Okay, the other type of intermolecular force are dipole-dipole forces. These are much stronger and they're more permanent than London forces. And what's going on is that because of polar bonds and polar molecules, these dipole-dipole forces occur because areas of positive charge of one molecule are attracted to areas of negative charge of another molecule. And there is a special kind of dipole-dipole force. This is called hydrogen bonding, and it's most commonly seen in water. And on Monday, we're going to do a lab where you get a chance to kind of experience, I'll put that in air quotes, experience what hydrogen bonding might feel like and why water it really exhibits these hydrogen bonding. And that is all that I have for intermolecular forces in real versus ideal.